show a relatively conserved dependence of metabolic rate on temperature. That is, the slope is pretty much similar across a wide range of taxonomic groups. So we're going to represent this in a fairly traditional way, just to say that the demand for oxygen is proportional to this kind of quasi-exponential function of temperature. It also depends on the body size, with some allometric exponent epsilon here, and on some kind of baseline metabolic rate, which, as usual, will depend on the particular physiology of the organism of interest. Okay, but the main step here is to say that what matters is the ratio of oxygen supply to demand. And we can construct that just from those simple kinds of scalings, and we're going to denote it with this symbol phi. So the symbol phi is just the ratio of those two previous expressions. So it involves the partial pressure of oxygen in the ambient water, the temperature, which enters through that exponential thing. So those are two properties of the environment that should influence the supply to demand ratio. Higher oxygen means higher supply, higher temperature means higher oxygen demand. But it also depends on three or several quantities actually that characterize the physiology of the organism. It's metabolic dependence on metabolic rate dependence on temperature, this E0, the body size, and the difference between the allometric scaling for supply relative to demand, and then some constant that depends on the gas exchange constant and the baseline metabolic rate. Okay. Lots of stuff in here that you don't really need to worry about, but I just want to show you how this index is constructed. And the key thing is that if we could estimate these parameters, which will depend on the species of interest, and we can just simply measure, of course, these properties in the environment, then we ought to be able to, for any given water parcel in the ocean, estimate the ratio of oxygen supply to demand. The problem is, of course, how to get those physiological constants. That's the first problem. But before going into that, I want to point out that one can interpret this quantity as the oxygen supply to demand. That's how it's constructed. But it also has another meaning, and that is that it's the ratio of the amount of metabolic energy conversion that could be sustained relative to what one would need at rest. I should have said before that we're going to use resting metabolism to estimate these resting metabolic rates. And what that means is that in a resting state, the value of phi equals 1 means that supply and demand are exactly matched. And that's kind of a threshold value, because if phi falls a little bit below that, you've got to do something like go into metabolic suppression, or mortality is going to increase. If phi is above that, it means that there's an extra bit of oxygen available that you could, use more energy from. Okay, so here's a kind of cartoon diagram of power output in an animal over different durations, and resting metabolic rate would be this constant curve. And the key thing is out here over time scales, of days or weeks or months or so, there needs to be some kind of sustained metabolic rate that is above the resting rate, otherwise you would never be able to get anything done. So at rest, phi of 1 is the absolute lower limit for physiological survival. If it goes below that, you're toast. But you need more than that, right? You need more than to just be able to sit around. You need some phi to be above that by some amount we're just going to call phi crit. So a critical amount of extra energy that you need if you want to actually survive in an ecosystem. You got to be able to run away and mate and all those kinds of things. Okay, now the thing is that this ratio has effectively been measured. The active metabolic rate relative to the resting rate has been measured for a whole variety of terrestrial species, terrestrial taxonomic groups, dozens and dozens of them. And this is just from a review paper that characterized those ratios, okay? So for birds, mammals, lizards, typically almost all the values fall between 1.5 and 5, okay? There's some extreme outliers, 7. And even for humans, I thought it was kind of amusing. We're just like everything else. Our actual daily metabolic demands are about 1.5 to 5, let's say, times greater than they would be at rest. Also amusing, actually my favorite part of this paper otherwise just a review of older studies, is that there was a particular job description associated with this range, and the lower limit was a scientist, and I'm pretty certain it was a modeler. The upper limit was a Tour de France cyclist, so I'm definitely on the lower limit. In any case, the point is we have a reference frame for evaluating active to resting metabolic ratios if we could figure out what they are for marine species. So to do that, we first need to get those parameters, okay? And I'm just going to kind of cruise through this briefly because it's just not, I'm hoping you'll take my word for some things. We can get those parameters by basically going to the literature and pulling out the data on either lethal or anaerobic critical oxygen levels and correlating them against inverse temperature. And that gives us, for example, the slope and intercept of the metabolic index. Once we declare that at these kind of lethal or anaerobic onset levels, we must be having a condition in which phi is 1. That's what caused them to start anaerobic metabolism and ultimately to increase mortality. And that, in fact, accounts for about 80% of the variance in hypoxic tolerance limits. Of course, we need to do that in a mass normalized way, and the mass normalization illustrates one other interesting thing, which is that as body mass increases, the critical oxygen pressure tends to increase, although that's not a universal finding. For all the species I'm going to talk about, it was either a flat line or a slightly increasing line, and an increasing line indicates that it's better to be smaller. That is, your likelihood of oxygen starvation is less if you're small. Okay. So here's what a map of the metabolic, with those parameters now, we can actually just map out using climatological data the metabolic index. Okay, now it's going to depend on the species that you're looking at. The map will have different values. But interestingly, if you normalize it to some particular regional average, as I've done here, I've taken the local value everywhere, and I've just divided by the average tropical value. For all those species, the map looks virtually indistinguishable. It's the exact same map, it's just rescaled by different actual values. So the relative distribution of metabolic index is the same for all the animals that we looked at, and the fundamental reason is that these slopes were all about the same. Okay? So what we find is that with the tropics by construction about 1, the high latitudes are about between 10 and 20. That is, there's about 10 times as much, if the tropics are defined to have about as much oxygen as you would need in a resting state to stay alive, the high latitudes have about 20 times more than you'd need. Okay? So that just sets up a gradient. And the reason why the gradient is so large with latitude is that the tropics are characterized by 2 conditions that are bad for a metabolic index. A, it's warm, and B, it's low oxygen. So there's less oxygen than you might need to do metabolism, and your metabolism is metabolic rate is relatively high. So what this suggests is that if we want to look at how oxygen and temperature combine to restrict habitats for marine species, looking at their latitudinal range limits would be a good idea. Okay. Now, you could also try to do it with vertical range limits, and that's a very interesting thing to do, but it's also much harder. And the reason is that the vertical variation in the metabolic index can sometimes increase with depth, and it can sometimes decrease with depth. It all depends on whether oxygen is declining more rapidly with depth than temperature, or vice versa. Of course, they both decline with depth, but if you're in places like an oxygen minimum zone, oxygen is decreasing, your oxygen supply decreases much more quickly than your oxygen demand, because oxygen is decreasing really sharply. In lots of other parts of the ocean, the reverse is true. The thermocline is so strong, temperature, your metabolic demand decreases faster than your oxygen supply should decrease. So this gives us a mixed picture for whether we would find the metabolic index to explain vertical range limits. And I'm just going to set that aside for now. Okay, so what we've done is to walk through as many of those species as we can and just map their metabolic index. And over the top of that map, just place dots wherever that species is actually observed. So this is the example for Atlantic cod. The colors indicate its metabolic index. Sorry for the small numbers, but it goes from 0 up to 10. Okay? And the blue stippling indicates where cod is typically found. The black line indicates a particular value of the metabolic index that lines up with the southernmost range boundary of Atlantic cod. And you can see that it basically follows the range boundary, sort of northward, then a little kink, then northward again, in the western side of the Atlantic. And it also hits the southern boundary over here in the eastern population of cod around the UK. Now, that particular value of the metabolic index depends on exactly what size you think cod need to be the sort of critical determinant of viable population. It should be some kind of mass at maturity, something like this. It also depends on exactly what season you think is important. But with all those uncertainties in the mix, you get that this value lies something along a value of about 2.8 to 4.3 for cod. So something like, let's say, 3. A value of metabolic index of 3 defines the boundary between where you find cod and where you don't. Okay? Now, cod are a nice single example because we can actually look at seasonal variability and cod migration to get some slightly better constraints. And I'm not going to go through this very much, except to say that that people know where cod migrate in the eastern along the eastern seaboard here, and they migrate from about 37 degrees latitude during the winter toward something like 41 degrees latitude in the summer, based on NOAA surveys. And that's exactly the latitude range and the timing at which we find that same value of the critical metabolic index. So the cod are moving in a way that matches what their metabolic index of something like, between 2.8 and 4.3. It's also true that although it's less well observed, there's a vertical migration in eastern cod populations, and it also follows the seasonal deepening and shoaling of the critical metabolic index of between 2.8 and 4.3. Okay, so what this says to us is that this metabolic index seems to be a reasonable candidate for an operative constraint on the latitudinal range limits of Atlantic cod. And in fact, we did this for a few other species, and we got the same answer, that the southern latitudinal limit of the species, including fish and crustaceans, was always at a metabolic index of something between, say, 2 and 5. Okay? So for all the species we were able to see, they stopped living in waters where the oxygen was unable to supply at least 2 or 3 times what they would need to stay alive in a resting state. Okay? Now those numbers hopefully sound a little bit familiar because they're basically the same kind of numbers that terrestrial ecologists have found for the active to resting metabolic rate ratio in all kinds of terrestrial species. So we think that this actually is indicating that the combination of oxygen and temperature as it influences supply to demand ratios is the operative constraint on how far south these northern hemisphere species can go. I'm beeping. It's okay? Okay. All right. Now, that gives us a... Let me know if I'm on fire or something. Otherwise, I'm just going to carry on. Okay, so that gives us a kind of starting point for trying to think about how habitat gets lost in a warming climate. And I'm going to kind of skip over that because it's not the most interesting part of this for me, except to say that if we take those projections of temperature change and oxygen change, we find that on average, globally, the metabolic index goes down by about 20%, and it goes down by much more in certain areas like the high latitude North Pacific. It goes down everywhere, though, pretty much. We can convert that into actual volumes of contemporary habitat that then fall below that critical metabolic index. and we get numbers that are comparable to that. Something like 20% of the current volume of habitat for all the species we can look at disappears in the next 100 years. Okay, so to conclude the first part, the oxygen supply to demand ratio, we think we can map with a certain amount of physiological, climatic, and demographic data. Species that are relatively diverse, have different hypoxic tolerances, all seem to be limited in their southern range boundary by an energetic requirement for something like 2 or 3 or 4 times their resting energy requirement. And that predicts a quantifiable contraction of marine habitat. Now, maybe the beeping was to let me know that I'm way behind schedule.
No, that's not what
You're good.
Okay, good. Okay, well, it's a kind of beep that I often need, but thanks for... So, part 2, and this one's going to be a little bit shorter. The question to remind you was, does climate... So we've hopefully established that climate warming, there's a good mechanistic data-based expectation that climate warming leads to the contraction of macrofaunal habitat, but you might say, but at least it'll be good for the microbes, right? Because anoxic zones should expand. Lots of people expect this. And what I want to do in part 2 is ask, well, okay, but will it really happen? The models have given us some indication that it's not so clear-cut, and we might like to know why and whether we should believe them. Okay, so to do that, I'm going to be simulating the past in a numerical ocean model and comparing what that kind of model predicts to actual sedimentary proxies for the rate of denitrification in the Pacific Ocean. All right, so to define what I mean by a model, it's a global model of the oceanic general circulation with a simple ecosystem embedded in it and biogeochemistry, most notably for the nitrogen cycle. And so what this does is you tell it what you think the winds have been over the historical period, which we know from reanalysis of weather data, and you put those winds in at the ocean surface, and it of course causes the ocean to circulate around, and you put in heat fluxes and freshwater fluxes, all the stuff that Bill was talking about earlier, and you just let the ocean respond to those changing conditions. And as it does, the ecosystems in this model ocean also begin to respond. So the productivity goes up and down and things of that nature. And the oxygen goes up and down. So we're simulating oxygen here, shown on this panel. Here's your shoaling hypoxic boundary here, getting near the equator. And up here we're showing the evolution of isotopes of nitrogen in the sinking flux of organic detritus. And we only need that so that we can compare the model simulations to the sediment record, and I'll talk more about that in a moment. And then this is just the thickness of that anoxic zone that the model predicts. Okay, so here's what we find when we do this model simulation over the past, since the International Geophysical Year, 1958, till almost the present, although an ever-receding present. We find that the volume of low oxygen water goes up and down quite a lot, okay? And it goes up and down no matter what volume, what oxygen threshold you use, but it goes up and down the most if you're interested in the anoxic part of the water column, between its peak volume, 40% above the normal, and its minimum volume, 30% below. There's something like a twofold contraction and then expansion of the anoxic zone, in this case in the Pacific Ocean, over the past 50 years. Okay? Now, when we first did these simulations, all we had to compare to was actual concentrations of oxygen from the California fisheries studies that Francisco told us about, starting with the collapse of the sardine fishery here. And they show that oxygen went up and then it went down in a way that mimics this, except it's a mirror image, because this is the volume of low oxygen water and this is the oxygen concentration. So when oxygen concentration is high, we expect the volume of low oxygen water to be low. But it's a circumstantial kind of comparison at this point. Still, worth exploring why that happens. It's a very strong response of the ocean, and it's very much not unidirectional. There's obviously some big mode of variability happening to drive this thing up and down like that. Whoop. Do I just hit? Did I do that?
Just check your laptop
Okay.
and restart your PowerPoint.
Uh-oh.
6 more.
Oh, Microsoft PowerPoint has encountered a problem.
That means we can restart it.
Yes. Great.
Explore it. Stand by. Yeah, so the other thing that was beeping was this thing, so that's,
Oh.
you're okay there.
Okay.
It's just your
Okay.
computer.
Sorry for the delay. Okay, so I'm going to speed this up a little bit. We can go into the model and diagnose why that happens. The answer in a nutshell is that respiration in the deep ocean was strong in the beginning, and then it got weak, and then it got strong again. Okay? Now, there was nothing in the model to make respiration do that except for what was imposed by the changing winds and circulation patterns. Okay? And what they did was they made that thermocline, that boundary between the warm water and cold water sphere, move up and down in the eastern Pacific where the anoxic zone is. And when the thermocline was shallow, we had strong respiration and a big anoxic zone. When the thermocline deepened, we got weak respiration and a shrinking anoxic zone, followed by the reverse pattern back to the earliest kinds of levels. Okay, so the mechanism in a nutshell is that something causes the thermocline to get shallow, and that's upwelling, to put a word on it, which drives more phytoplankton productivity, more export of organic matter, more respiration in the deep ocean, and the whole anoxic zone expands. Then when whatever happens to cause upwelling to reduce, the thermocline relaxes down, there's less nutrients coming up to the surface, the whole thing weakens again. Okay? And you can identify phases of the Pacific decadal oscillation that favor one pattern or the other, but I'm not going to get into that. Okay, what I do want to get into is a test that this actually happened. It's not just a model artifact. Okay, so here's that measure of the nitrogen that's been removed by microbes. Again, zooming in on the tropical Pacific, nitrate. This is oxygen here, low oxygen, and here's the strongest nitrate deficits in the white lines, eastern tropical North and South Pacific. And here are 3 places where my geochemist colleagues drilled cores, sliced them up, and measured the N15 to N14 ratio of bulk organic nitrogen over the past 150 years, dated with lead-210. Okay, I'm jumping the gun a little bit. Why would they do that? They do that